So, while in the previous example, we saw a constructive existence proof, let's look at an example now of a non-constructive existence proof. So here I've written out the example. We have to show that some digit in the decimal expansion of the square root of 2 occurs infinitely often. And so you can see this is indeed an existence proof because I'm trying to find some digit such that some statement is true. And that statement is it occurs infinitely often in the decimal expansion of the square root of 2. So how are we going to go about doing this if we wanted to do it in a non-constructive fashion? Well, with a non-constructive existence proof, we have to argue why such an x must exist. So we have to make some sort of argument. So here, my proof is going to be an argument. And so what kind of argument am I going to use? Let's try an argument by contradiction. So once again, in search of a contradiction, I'm going to assume the negation of this statement right here and see if that leads to some sort of contradiction. So what's the negation of the statement? Show that some digit occurs infinitely often. So thinking about it in that form, the negation of that statement would then be every digit in square root of 2 occurs finitely often. So I've assumed the negation of my statement, say every digit in the decimal expansion of the square root of 2 occurs finitely often. So if we think about that, what does that mean? Well, if it occurs finitely often, that means that the decimal expansion of the square root of 2 is actually going to have to terminate somewhere. So that would imply we could write the square root of 2 as, well, let's start writing down some of its digits. 1.41 ... And then at some point, since every digit occurs finitely often in our argument right here, it's going to have to end. I don't know where it ends, and I don't know what digit it is, so I'm going to call that last digit xn. So that here is my last digit. And how might we derive a contradiction from this? Well, we know something about the square root of 2. We've actually already in previous videos showed that the square root of 2 is irrational. And looking at this, if I have a finite decimal expansion, I could simply rewrite this thing. I could rewrite this thing as 141 ... whatever the other digits are, all the way down to my very last digit xn, and then I divide that by 10 to the n plus 2. And you'll notice that on the top here, we have an integer, and on the bottom, we have an integer. Well, an integer divided by an integer, that's a rational number. But that's a contradiction, right? Because we've already showed that the square root of 2 is an irrational number. And so I'm actually finished with my proof. I have argued in search of a contradiction, say that every digit occurs finitely often, and I've been able to derive my contradiction. So my proof here is complete. But it's a really interesting kind of proof, right? Because it asked us to show that some digit occurs infinitely often. And I've argued and showed that, well, if that wasn't the case, that would lead to a contradiction. So some digit has to occur infinitely often, but I did not actually show you which digit occurs infinitely often, or which digits occur infinitely often. That is the hallmark of a non-constructive proof. I've not actually told you which digit occurs infinitely often. I've simply given you an argument about why such a digit must exist. So while that was a constructive argument, and you have an explicit x and y that shows that your statement is true, here I've just given you an argument about why it has to be true, and I've never actually demonstrated for you the specific x that would make p of x true. So this is an example of a non-constructive proof. And we'll go ahead and look at a couple more examples of both constructive and non-constructive existence proofs in future videos.